There is a direction in space that humanity has barely explored, not outward toward the planets and not onward toward the stars, but perpendicular to the entire architecture of the solar system. Every major planet orbits within a relatively thin, flat disk called the ecliptic plane. For billions of years, nearly everything that formed around the Sun remained confined to this cosmic pancake. Yet above and below that plane lies a vast region of space that only a handful of spacecraft have ever sampled. The reason is surprisingly simple. Every spacecraft launched from Earth inherits Earth's orbital velocity of nearly 30 kilometers per second around the Sun. To travel directly out of the solar system's plane, a spacecraft must overcome much of that sideways motion, a maneuver that demands enormous amounts of energy. As a result, most missions follow the ecliptic rather than leaving it. What lies beyond this overlooked direction is a different perspective on our solar system, the surrounding interstellar environment, and the structure of the galaxy itself. Exploring it reveals how much of our cosmic neighborhood remains largely unseen, why the solar system is flat, and what that means for everything below it. The flatness of the solar system is the most important geometric fact about the place we inhabit, and it is simultaneously one of the most overlooked. Every diagram of the solar system that most people have encountered, the Sun at the center, with the planets arrayed in concentric rings around it, presents this flatness as the default, as if it were the obvious and expected arrangement. It is not. It is the specific outcome of a specific physical process that occurred 4.5 billion years ago. And understanding that process is the starting point for understanding what lies beyond the system's flat edge, and why getting there is so difficult. The solar system formed from a vast, slowly rotating cloud of gas and dust called the solar nebula. This cloud was not initially flat. It was a rough sphere of material, loosely organized, extending across many light years of space. But it was rotating slowly and perhaps unevenly, with a slight net angular momentum accumulated over billions of years of interaction with surrounding material in the galaxy. When the cloud began to collapse under its own gravity, the rotation became critical. Along the axis of rotation, there was nothing to prevent collapse. Gravity pulled material inward and nothing pushed back. But perpendicular to the rotation axis, material could not simply fall inward, because angular momentum had to be conserved. As the cloud contracted, any material in the equatorial plane moved faster and faster in its rotation, and the outward centrifugal effect of that rotation resisted the inward pull of gravity, preventing complete collapse in that direction. The cloud could fall along its polar axis, but not across its equator, and the result was exactly what angular momentum conservation always produces when combined with gravity: a disk. A flat, rotating disk of gas and dust, with the young Sun forming at the center and the planets coalescing from the material that remained in the disk's plane. This process is not unique to our solar system. It happens wherever gravity and rotation combine with a collapsing cloud of material. The rings of Saturn are a small disk. The disk of the Milky Way galaxy is a large one. Accretion disks around black holes are disks that are governed by the same physics at very different scales. Flatness in any gravitationally organized rotating system is not a coincidence. It is the expected outcome of the physics, and it has been locked into the solar system for the entire 4.5 billion years of its history. The disk the planets formed in, called the protoplanetary disk, eventually dispersed. The young Sun's radiation pressure and stellar wind swept away most of the remaining gas and dust over the first few million years of the solar system's existence. But the planets that formed within the disk retained the disk's geometry, continuing to orbit in the same plane where they were born, held there by the angular momentum they inherited from the original cloud. The plane they orbit in is called the ecliptic, defined as the plane of Earth's orbit projected outward onto the sky, and it serves as the reference plane for essentially all discussions of solar system geometry. The other planets orbit within a few degrees of the ecliptic, Mercury tilts by about 7 degrees, the most of any major planet. Venus and Mars tilt by less. Jupiter, Saturn, Uranus and Neptune all orbit within a few degrees of the ecliptic as well. The solar system is, by any reasonable standard, flat, but not perfectly flat. The dust and small debris that fill the solar system remain in this disk, replenished by collisions in the asteroid belt and by the gradual erosion of comets as they pass near the Sun. This dust scatters sunlight, creating a faint glow along the ecliptic visible from Earth on very dark, clear nights, as a soft cone of pale light rising from the horizon after sunset or before sunrise. This zodiacal light, as it is called, is sunlight reflected off the solar system's own dust, a physical marker of the disk in which the planets orbit. Looking along the plane of the ecliptic from Earth is looking through this dust-filled disk with all the scattered light it produces. Looking perpendicular to the disk, either above or below it, is looking through much less dust, and the sky is correspondingly cleaner, darker, and more transparent to faint sources from the distant universe. This is the first and most immediate consequence of the solar system's flatness for anything attempting to travel below it. Below the ecliptic is away from the disk, away from the dust, away from the concentrated material that fills the plane and scatters light. The sky below the solar system's floor is, in a very specific physical sense, cleaner than the sky along the ecliptic, and the view it offers of the rest of the universe is correspondingly less contaminated by our own solar system's foreground. The region below the solar system is scientifically valuable for this reason alone, independent of whatever specific objects might be encountered along the way. But there are specific objects to be encountered, beginning at the innermost layer and extending outward to progressively more remote and stranger environments. And tracing what they are and what they would tell us is the central project of everything that follows. The Sun itself is at the center of this geometry, and its own structure reflects the disk in a way that is not immediately obvious. The Sun rotates, completing one full rotation roughly every 25 days at its equator, though it rotates more slowly at higher latitudes because it is not a solid body. This differential rotation, faster at the equator and slower at the poles, is one of the engines that generates the Sun's magnetic field through a process called the solar dynamo. The Sun's magnetic poles, the regions where the global magnetic field converges, are located at the Sun's geographic poles, directly above and below its rotation axis. The solar poles are the places where the Sun's magnetic field lines emerge most cleanly, where the fast solar wind originates, where the structures called polar coronal holes open up and allow the Sun's outer atmosphere to stream freely outward into space. These polar regions of the Sun are located in the direction directly above and below the solar equator, which is closely aligned with the ecliptic. To look at the Sun's poles directly, you must be above or below the disk. From Earth, inside the disk, the Sun's poles are foreshortened, seen at a shallow grazing angle where all their structure is compressed and distorted by perspective. The view directly below us, the first destination on any downward journey, is a direct view of the Sun's south pole that no spacecraft has ever been able to hold for more than a brief passing glimpse. The inherited velocity that locks everything in the plane. Every spacecraft ever launched from Earth shares a single fundamental property before its engines fire a single time. It is already moving at approximately 30 kilometers per second in the direction of Earth's orbital motion around the Sun. This velocity is not chosen by engineers or selected by mission planners. It is inherited automatically and unavoidably from the planet the spacecraft is launched from. Earth moves around the Sun at 30 kilometers per second, completing one full orbit every year. The launch pad, the rocket sitting on it, the spacecraft inside the rocket, the fuel in the tanks, all of it is moving at 30 kilometers per second relative to the Sun before the countdown begins. At the moment of launch, the spacecraft inherits this velocity instantly and completely. There is no way to avoid it. This inherited velocity is enormously useful for missions that want to travel within the plane of the ecliptic. A spacecraft heading to Mars, for instance, can use Earth's 30 kilometers per second of orbital velocity as a free head start. The spacecraft only needs to add a relatively small amount of additional velocity, roughly 4 kilometers per second, to stretch its orbit outward from Earth's orbit to Mars's orbit. It is surfing the current of Earth's orbital motion, adding a small push in the right direction to redirect that existing momentum onto a new path. The same logic applies to missions to the outer planets. Every mission to Jupiter, Saturn, Uranus and Neptune has exploited Earth's orbital velocity as a free initial push, with the spacecraft's engines providing only the incremental change needed to reach the target orbit. This is why missions to the outer solar system are technically possible with the rockets we have built. The large velocity needed to reach these destinations is provided mostly for free by Earth's orbital motion. The rockets only need to add a small fraction on top. But travelling below the ecliptic, perpendicular to Earth's orbital motion, is a completely different problem. To move truly downward, out of the plane of the ecliptic, a spacecraft must first cancel its 30 kilometers per second of inherited sideways motion and then replace it with an equal downward velocity. The sideways motion is not useful for a downward journey. It is a liability. Every kilogram of spacecraft is moving sideways at 30 kilometers per second, and changing the direction of that motion to point downward requires applying a force perpendicular to the current velocity, which is the most expensive kind of maneuver in orbital mechanics. The delta V, the change in velocity required, is not a small incremental adjustment on top of an existing useful velocity. It is the full cancellation of 30 kilometers per second of sideways motion and its replacement with 30 kilometers per second of downward motion, for a total velocity change of roughly 42 kilometers per second, comparable to the square root of 2 times 30. To understand how large this number is, consider that the most capable chemical rockets humans have ever built have delivered total delta V budgets to their payloads of roughly 15 to 20 kilometers per second over the entire course of a mission, using multiple stages and gravity assists over years of flight. 42 kilometers per second of delta V from low Earth orbit is not achievable with any chemical propulsion system that exists or is likely to exist. The Tsiolkovsky rocket equation, which describes the relationship between propellant mass and achievable velocity change for any rocket, makes the impossibility quantitative. To achieve 42 kilometers per second of delta V using the best available chemical propellants, the rocket's initial mass, including all propellant, would need to be roughly 10,000 times the final mass of the spacecraft. There is not enough material in any feasible spacecraft to carry this much propellant. The direct downward trajectory is beyond chemistry. This is why, in the entire history of spaceflight, no spacecraft has ever climbed to more than a small fraction of the 90 degrees of inclination relative to the ecliptic that would constitute a truly polar solar orbit, except by using gravity assists. The 2 missions that have reached the highest inclinations above and below the ecliptic both use Jupiter's gravity as a slingshot, trading a journey to Jupiter for the massive inclination change that only Jupiter's enormous gravity well can provide for free. Even with Jupiter's assist, neither reached a full 90-degree inclination. The maximum achieved was roughly 80 degrees, close to but not exactly perpendicular to the ecliptic. A true polar orbit around the Sun, one that passes directly over the Sun's poles and therefore directly above and below the ecliptic plane, has never been achieved by any mission. The difficulty of escaping the plane of the ecliptic is, in a very direct sense, a consequence of the same physics that created the plane in the first place. The angular momentum that caused the solar nebula to flatten into a disk 4.5 billion years ago is still present in the solar system today, distributed among the planets and their orbital motions. It cannot be destroyed. It can only be transferred. Every spacecraft that tries to escape the plane must fight against this angular momentum, and the energy required to do so reflects the energy that was originally deposited into the disk's rotation billions of years ago. The plane is not a feature of the solar system that we happen to live in. It is a consequence of the conservation of angular momentum across cosmic time, and escaping it means acting against one of the most fundamental conservation laws in physics. That is not impossible, but it is expensive in the specific currency of space travel, which is velocity change, and the bill is one that no chemical rocket can pay. The perihelion burn, the trick that makes escape possible. There is an elegant solution to the problem of escaping the ecliptic plane that does not require cancelling 30 kilometers per second of inherited velocity in a single brute force maneuver. The solution is counterintuitive on first encounter, but becomes almost inevitable once the underlying physics is understood. The trick is to fall toward the Sun before trying to climb away from the disk, falling inward toward the deepest available gravitational well in the solar system, and then burning the spacecraft's engine at the moment of closest approach extracts far more velocity change from the same amount of fuel than any burn performed at Earth's distance from the Sun. The principle has a name, the Oberth effect, after the early 20th century rocket pioneer Hermann Oberth, who first described it quantitatively, and it is one of the most powerful tools available to trajectory designers working with limited fuel budgets. The physics behind the Oberth effect is rooted in the relationship between kinetic energy and velocity. Kinetic energy scales with the square of velocity. An object moving at 100 kilometers per second has 100 times the kinetic energy of an object moving at 10 kilometers per second, not 10 times, because kinetic energy goes as the square. When a spacecraft falls toward the Sun under gravity's influence, it accelerates enormously. At a perihelion distance of a few solar radii, a spacecraft can be moving at hundreds of kilometers per second relative to the Sun. When the engine fires at this moment of maximum speed, the thrust produces a change in velocity that is relatively small in absolute terms, perhaps a few kilometers per second of delta V. But because the spacecraft is already moving so fast, the energy gain from this small velocity increment is enormous, because energy gain equals the thrust times the change in speed, and the energy scales with the square of the final velocity minus the square of the initial velocity. At very high speeds, even small velocity increments produce large energy gains. The same amount of fuel burned at this high speed does far more useful work than the same fuel burned at the slower speeds typical of Earth's distance from the Sun. For the specific problem of escaping the ecliptic plane, the perihelion burn offers a dramatic reduction in the required fuel. Calculations have shown that a trajectory that first falls inward to a perihelion very close to the Sun, and then performs the inclination-changing burn at that perihelion, can achieve a polar solar orbit for a delta V cost of roughly 5 to 8 kilometers per second, compared to the 42 kilometers per second required for a direct perpendicular thrust from Earth's orbit. The savings come from performing the maneuver at the point where the spacecraft is moving fastest and where each unit of fuel does the most work. The trajectory takes longer because the spacecraft must first travel inward to the Sun before it can begin climbing out of the plane, but the fuel savings are so dramatic that this approach is the only practically feasible route to a polar solar orbit with any foreseeable propulsion technology. The practical implementation of the perihelion burn for ecliptic escape requires solving a separate engineering challenge, surviving the thermal environment very close to the Sun. At a perihelion of a few solar radii, the solar flux is thousands of times what Earth experiences, and any spacecraft approaching this close must be protected by a specialized heat shield capable of reflecting or absorbing this enormous energy input, without allowing the temperature behind the shield to reach levels that damage the instruments or structure. This challenge has been demonstrated to be solvable. The Parker Solar Probe, launched in 2018, approaches the Sun to within approximately 9 solar radii at its closest passes, experiencing solar flux intensities hundreds of times greater than at Earth's distance, protected by a carbon composite heat shield that keeps the spacecraft body at manageable temperatures while the shield's front face reaches temperatures above 1,000 degrees Celsius. Future missions designed to perform perihelion burns for ecliptic escape would need to approach even closer, perhaps to 3 to 5 solar radii, where the thermal environment is considerably more extreme. But the basic engineering approach has been validated. A gravity assist from Venus offers another path toward high ecliptic inclinations that is less dramatic than the perihelion burn, but more practical for near-term missions. By flying close to Venus repeatedly, a spacecraft can accumulate inclination changes over multiple passes, each adding a few degrees of tilt to the orbit. The process is slow, requiring years of repeated Venus flybys before significant inclination is achieved, but it requires no exotic thermal engineering and no extreme perihelion passes. The current solar orbiter mission from the European Space Agency uses repeated Venus gravity assists to gradually raise its orbital inclination, currently approaching 30 degrees above the ecliptic and expected to reach higher inclinations over the coming years. Solar Orbiter is the most successful contemporary example of a spacecraft climbing out of the plane of the ecliptic using repeated planetary gravity assists, and its gradual progress toward higher inclinations is providing the most detailed images of the Sun's polar regions ever obtained, though it has not yet reached the true polar perspective that a full 90-degree inclination would provide. Solar sails offer a third approach that is fuel-free but requires patience. A spacecraft equipped with a large, highly reflective sail can use the continuous pressure of sunlight to gradually change its orbit over months and years. By orienting the sail at specific angles relative to the Sun, a sailcraft can add or subtract energy from its orbit, tilt the orbital plane, or spiral inward or outward without consuming any propellant at all. The thrust available from sunlight pressure is very small, comparable to the weight of a few coins on a square kilometre of sail. But it is continuous and free, and over years of operation it accumulates into significant orbital changes. Proposed solar sail missions to high ecliptic inclinations have been studied extensively and shown to be technically feasible, with the primary limitation being the size and deployment reliability of the sail structure required, and the patience demanded by the slow accumulation of tilt over years of flight. The combination of a solar sail for the initial inward spiral and a small chemical engine for the perihelion burn represents perhaps the most efficient overall approach, minimizing the fuel required while accepting a longer mission timeline in exchange. The Sun's south pole, what has never been properly seen. The first significant object encountered on a journey directly below the ecliptic is the Sun itself, or more precisely, the Sun's south pole, the geographic bottom of the star around which everything in our solar system orbits. This seems like it should be well observed. The Sun is the closest star to Earth by an enormous margin, so bright it can be seen in daylight, so large it fills half a degree of sky, studied by astronomers for centuries, with instruments ranging from simple pinhole cameras to space-based ultraviolet telescopes. And yet the Sun's south pole, specifically, has never been photographed properly. It has never been mapped in detail. The structure of the magnetic field at the southern polar region, the dynamics of the atmosphere above the South Pole, the detailed character of the polar coronal holes that open up over the poles and allow the fast solar wind to stream outward. All of these remain poorly constrained by observation, because observing them requires a vantage point that no mission has sustained. From Earth's position inside the ecliptic, the Sun's south pole is always seen at a foreshortened angle. The geometry of Earth's orbit means that the South Pole is never tipped directly toward us at any point in the year. At best, due to a slight 7-degree tilt of the Sun's rotation axis relative to the ecliptic, the South Pole tilts marginally toward Earth during part of each year, allowing a view at an angle of perhaps 7 degrees below the equatorial plane. At this angle, everything near the pole is compressed by perspective. Features that are spread across 10 degrees of solar latitude near the pole appear compressed into barely 1 degree of apparent angular extent on the observed disk. The fine structure of the polar magnetic field, the boundaries of the polar coronal holes, the individual polar plumes that extend outward from the polar region, all are hidden within this compression, appearing as a narrow smear at the solar limb rather than as the rich, detailed landscape they actually constitute. The specific scientific questions that a direct South Polar view would address are not minor refinements to existing knowledge. They concern some of the most fundamental aspects of how the Sun operates. The Sun's magnetic field reverses its global polarity approximately every 11 years as part of the solar activity cycle. At the height of this reversal, the north and south magnetic poles temporarily disappear and then reappear with opposite polarity. The reversal originates in the polar regions, where the accumulation of magnetic flux from lower latitudes gradually overwhelms the existing polar field and causes the switch. Understanding exactly how this process unfolds in spatial and temporal detail requires observing the polar regions continuously and at high resolution throughout the cycle. No mission has been able to do this. The few fleeting glimpses of the poles provided by the two missions that have reached high ecliptic inclinations have revealed enough to demonstrate that the poles are scientifically extraordinary, but nowhere near enough to characterize the reversal process in the detail that would allow reliable prediction of future solar cycles. The polar coronal holes are the source of the fast solar wind, the stream of charged particles moving at approximately 700 kilometers per second that fills the heliosphere and influences the space weather experienced by every planet in the solar system. From the Sun's equatorial regions, a slower, denser solar wind originates from the boundaries of closed magnetic field regions. The fast wind from the poles and the slow wind from the equator interact as they propagate outward, creating structure in the heliosphere that ultimately determines the radiation environment of Earth and the other planets. Characterizing the fast wind's origin more precisely, understanding how and where exactly it forms within the polar coronal holes, requires seeing the polar region directly. This is fundamental to space weather forecasting and therefore to the protection of satellites, power grids, and astronauts in space. The inability to observe the solar poles directly is not merely an academic gap. It has practical consequences for our ability to predict and respond to solar activity. The Solar Orbiter mission, the most advanced current attempt to observe the Sun's poles, has been providing the best images yet obtained of the polar regions as it gradually increases its orbital inclination through repeated Venus gravity assists. In late 2022 and early 2023, the spacecraft reached inclinations high enough to image the South Polar region at angles significantly better than those available from Earth. The images revealed a magnetic field structure at the pole that was finer and more complex than lower latitude regions, with countless small magnetic flux concentrations woven into a tangled network rather than the broad, organized magnetic patterns of the active regions at lower latitudes. Polar plumes were resolved as individual structures extending outward from the hole boundaries. It was the clearest view yet obtained of this region, and it immediately raised more questions than it answered about the dynamics and evolution of the polar field. The mission is expected to reach higher inclinations in the coming years, but it will never achieve a true polar orbit. Its maximum inclination, reached after many years of Venus gravity assists, will be approximately 33 degrees, still 60 degrees short of the direct overhead view that a polar orbit would provide. The fast solar wind and why the poles are where it comes from. The solar wind is not a uniform stream. From Earth's position inside the ecliptic, this fact is sometimes overlooked because the solar wind that reaches Earth is a mixture, a blend of contributions from different regions of the Sun's surface, arriving at Earth's orbit after being processed and mixed during their outward journey. But at the source, the solar wind has two clearly distinct populations with different speeds, different densities, and different compositional signatures, and the distinction maps directly onto the solar geometry. The fast wind comes from above and below. The slow wind comes from the middle. Understanding why requires understanding the structure of the Sun's magnetic field, and why the poles are different from the equator in a way that directly affects the plasma escaping into space. The Sun's magnetic field at the surface is extraordinarily complex and variable. Sunspots are concentrations of intense magnetic field that suppress convection and create the dark, cooler patches visible on the solar surface. Active regions surrounding sunspots contain loops of magnetic field arching upward from the surface and returning to it, trapping hot plasma in these loops and creating the bright, complicated structures visible in ultraviolet images of the corona. These closed magnetic loops, where field lines begin and end on the solar surface without opening into space, prevent the solar wind from flowing outward through them. The plasma in closed magnetic loops is trapped, contained, unable to escape into the heliosphere. The polar regions are different. At the Sun's geographic poles, the magnetic field does not form closed loops in the same way. Instead, the field lines at the poles point outward into space without returning to the surface. These open field lines create what astronomers call polar coronal holes, regions of the solar atmosphere where the corona appears darker because the plasma density is lower. The plasma in polar coronal holes is not trapped. It flows outward along the open magnetic field lines and escapes into the heliosphere as the fast solar wind. The polar coronal holes are, in the most literal sense, holes in the Sun's magnetic containment, openings through which the Sun's atmosphere can pour freely into space. The fast solar wind that streams from these polar holes has a speed of approximately 700 to 800 kilometers per second, roughly twice the speed of the slow wind that originates from the equatorial regions. It also has a different composition. It is less dense than the slow wind and has slightly different ratios of various heavy elements, reflecting the different physical conditions at its origin in the open-field polar regions. These compositional differences have been measured in detail by in situ spacecraft that have passed through different latitude ranges within the heliosphere, and they can be used to trace any particular parcel of solar wind back to its source region on the Sun's surface. The first direct confirmation that the fast wind originates from polar coronal holes came from the Ulysses mission, which used a Jupiter gravity assist in 1992 to redirect its orbit to high ecliptic inclinations, and then spent nearly 2 decades measuring the solar wind environment at different heliocentric latitudes. As Ulysses climbed to higher latitudes during the quiet phase of the solar cycle, it found itself increasingly in fast, uniform solar wind rather than the variable, structured slow wind it had been measuring at lower latitudes. The transition was not abrupt, but occurred gradually over a range of latitudes corresponding to the edges of the polar coronal holes. Within the polar region itself, the fast wind was remarkably smooth and uniform, compared to the turbulent, highly structured slow wind that Ulysses had measured at equatorial latitudes. This contrast confirmed that the polar regions produce a fundamentally different kind of solar outflow from the equatorial regions, and established the basic picture that still guides understanding of the bimodal solar wind. What Ulysses could not do, because it carried no camera capable of imaging the Sun's surface, was connect its in situ wind measurements directly to specific visual structures on the Sun. The mission could say with confidence that fast wind came from high latitudes and slow wind from low latitudes, but it could not observe the polar coronal holes themselves or watch the fast wind emerge from specific locations within the holes. This connection between the observable surface structure and the measurable wind properties requires simultaneous imaging of the solar surface and in situ sampling of the wind, ideally from a position close enough to the Sun that the wind has not yet been significantly modified by the expansion and interaction processes that occur during its outward journey. Solar Orbiter is designed to provide exactly this simultaneous imaging and in situ measurement from positions much closer to the Sun than any previous mission, and its preliminary results are already showing connections between specific surface structures and the wind properties measured by its particle detectors that were not previously resolvable. The fast wind from the solar poles does not just fill the heliosphere smoothly. As it propagates outward from the poles and spreads into the heliosphere, it encounters the slow wind from the equatorial regions at stream interaction regions where the two wind types collide. At these boundaries, the faster wind piles up against the slower wind ahead of it, creating compressed regions of higher density and stronger magnetic field. These stream interaction regions, as they propagate outward, can trigger geomagnetic storms when they reach Earth and can accelerate particles to high energies that create radiation hazards for spacecraft and astronauts. The structure of these interaction regions depends critically on the properties of the fast wind at its source, which depend on the detailed structure of the polar coronal holes that no mission has yet been able to observe directly and continuously. Every space weather prediction that involves the fast wind component ultimately traces back to the poorly observed polar source region, the heliospheric current sheet, and what it looks like from below. One of the most distinctive large-scale structures in the solar system is invisible to any optical telescope and can only be detected by spacecraft that fly through it. It extends through the entire heliosphere from the Sun outward to the heliopause, the boundary where the Sun's influence gives way to the interstellar medium. It separates the heliosphere into two magnetically distinct hemispheres, one with the Sun's north magnetic polarity and one with its south. It is not a physical surface in the conventional sense, but a mathematical surface, the locus of points where the Sun's magnetic field reverses direction, a boundary layer in the solar wind plasma. It is called the heliospheric current sheet, and from below the ecliptic, it would appear as a vast, slowly undulating membrane that fills the inner solar system, whose shape encodes the global state of the Sun's magnetic field at any given moment. The heliospheric current sheet forms because the Sun has two magnetic hemispheres, just as Earth does. The Sun's north magnetic pole and south magnetic pole are connected by field lines that arc through the corona and extend into the heliosphere. Above the north magnetic pole, the field points outward from the Sun. Above the south magnetic pole, the field points inward toward the Sun. Between these two regions, there must be a surface where the field neither points inward nor outward, but lies purely tangential, and this surface is the current sheet. The sheet is named for the fact that electrical currents flow within it, as required by Maxwell's equations whenever a magnetic field reverses direction across a thin boundary. In the simplest model of the Sun's magnetic field, where the field is a perfect dipole aligned with the rotation axis, the current sheet would lie exactly in the solar equatorial plane, a flat disk extending outward through the heliosphere. But the Sun's magnetic field is not a perfect dipole and is not aligned exactly with the rotation axis. The magnetic axis is tilted at some angle relative to the rotation axis, and the field at lower latitudes is complicated by the presence of active regions and their associated magnetic structures. The result is a current sheet that is warped, tilted, and in some phases of the solar cycle quite dramatically structured, resembling the wavy hem of a spinning skirt rather than a flat disk, which is why it is often described with the analogy of a ballerina's skirt. As the Sun rotates, carrying the warped current sheet with it, the sheet's ripples sweep past the planets, alternating between regions of inward and outward magnetic field, in a pattern that drives much of the variability in the solar wind environment at any fixed location in the heliosphere. From Earth, inside the ecliptic, spacecraft cross the heliospheric current sheet multiple times during each 27-day solar rotation, because the sheet's wavy structure carries its crests and troughs across Earth's orbital plane repeatedly. Each crossing is detected by the reversal of the magnetic field direction measured by the spacecraft's magnetometer, and the pattern of crossings can be used to infer the geometry of the current sheet at the time of observation. But this reconstruction is indirect, based on multiple point measurements spread over time, rather than a direct visual observation of the sheet structure as a whole. No spacecraft has ever been positioned to look at the current sheet from above or below and see its geometry directly. From a position below the ecliptic, directly beneath the solar system's floor, the view of the heliospheric current sheet would be something genuinely unprecedented. The sheet would appear not as a series of crossing events detected by magnetometers, but as an extended, visible structure filling the visual field. Of course, the sheet itself is not visible in optical wavelengths, but its presence can be inferred from the structures associated with it in the corona, particularly the bright streamers that mark the belt of closed magnetic field surrounding the equatorial region. During total solar eclipses, these streamers are the most prominent features of the corona, extending outward from the Sun in bright, blade-like sheets that trace the magnetic geometry of the current sheet above. From a high inclination vantage below the ecliptic, these streamers would appear in perspective, their true three-dimensional structure revealed in a way that the flat two-dimensional projection seen from inside the ecliptic cannot convey. During the quiet phase of the solar cycle, when the current sheet is relatively flat and confined near the solar equatorial plane, the streamer belt would appear from below as a wide, roughly circular halo around the equator of the Sun, with the polar coronal holes opening up clearly above and below it, and the polar plumes extending outward from the holes in a visible pattern. During the active phase of the cycle, when the current sheet is dramatically warped and tilted, the structure would be far more complex, with the sheet rising to high latitudes in some longitudes and dropping close to the equatorial plane in others. The spatial structure of the current sheet's warping is one of the key determinants of how different wind streams interact as they propagate outward, and seeing it directly from a high latitude vantage would provide constraints on solar wind models that cannot be obtained from point measurements alone. The relationship between the current sheet's geometry and the occurrence of geomagnetic storms at Earth is direct but poorly characterized. Storms tend to be more severe when Earth encounters regions of the solar wind where the magnetic field is directed southward, opposite to Earth's own northward pointing field at the magnetopause, because this anti-parallel configuration allows magnetic reconnection that channels solar wind energy efficiently into Earth's magnetosphere. The southward pointing regions in the solar wind are associated with specific structures in and near the heliospheric current sheet. Better characterization of the current sheet's geometry, made possible by high inclination observations, would improve the lead time and reliability of geomagnetic storm predictions in a way that has direct economic and safety implications for satellite operations, power grid management, and human spaceflight. The zodiacal cloud in plan view, seeing the dust disk from outside. One of the most scientifically informative things a spacecraft positioned below the ecliptic could observe is something that sounds almost mundane: the dust that fills the solar system. From outside the plane, the zodiacal cloud of fine dust particles that occupies the inner solar system would appear not as a faint glow along the ecliptic, but as an extended, flattened disk structure seen in plan view for the first time. This perspective would allow the three-dimensional distribution of the dust to be mapped, the contributions from different source populations to be separated, and the dynamics of the dust as it spirals inward under the combined influence of solar gravity and radiation pressure to be studied in a way that is completely impossible from inside the disk where the observer is embedded in the very thing being measured. The zodiacal cloud is created by several ongoing processes. The most important source in the inner solar system is collisions in the asteroid belt between Mars and Jupiter, which gradually grind asteroids into smaller and smaller fragments, and ultimately into the micron scale and millimeter scale particles that make up most of the dust. Comets contribute dust along their orbital paths as sublimating ice releases embedded solid particles during each close approach to the Sun. In the outer solar system, collisions among Kuiper belt objects produce a similar dust disk at larger distances. Interstellar dust, originating outside the solar system entirely, flows into the inner solar system from the direction of the Sun's motion through the galaxy. Each of these sources has a distinct spatial distribution and distinct dynamical properties that, in principle, allow them to be distinguished given observations from a viewpoint that can resolve the dust cloud structure. From Earth, the zodiacal cloud is seen as a glow because Earth is inside it. The sunlight scattered by the dust in all directions creates a background illumination that is brightest along the ecliptic, where the dust is densest, and fades toward the poles, where the dust is sparse. Specific structures within the cloud, such as the dust bands associated with families of asteroids produced by specific historical collisions, are visible as slight brightness enhancements within the general glow. But disentangling them from the background cloud requires careful subtraction and modelling. The geometry of the observations, looking through the dust along lines of sight that vary in path length and dust density, makes precise three-dimensional mapping difficult. From below the ecliptic, the geometry reverses. Instead of looking through the cloud along its longest dimension, a spacecraft below the disk would look upward at it from below, seeing the disk as an extended, roughly circular structure centered on the Sun. The brightest region would be near the Sun itself, where the dust density is highest, and the disk would fade outward to lower surface brightness at larger solar distances. The vertical structure of the disk, how rapidly it thickens with distance from the Sun, and how it is perturbed by the gravitational influence of the planets, would be directly visible. The dust bands from individual asteroid families would appear as concentric ring-like structures at specific radial distances from the Sun, superimposed on the general disk background. The enhancement in dust density in the inner solar system near Venus and Earth's orbital distances, where gravitational focusing and the slower in-spiral rate cause dust to accumulate, would be directly apparent. This is not merely a visual curiosity. The three-dimensional structure of the zodiacal cloud encodes information about the current balance of dust creation and destruction in the solar system, the history of major asteroid collisions, and the dynamics of how material spirals inward under the Poynting-Robertson effect, the slow drain of orbital energy that results from the asymmetric re-emission of absorbed sunlight. The Poynting-Robertson effect causes all dust particles in the solar system to slowly spiral inward toward the Sun on timescales that depend on particle size, eventually reaching the inner solar system where they are vaporized by the intense solar heating close to the Sun. This inward spiral means the zodiacal cloud is not in a steady state, but is being continuously replenished by new dust from asteroid collisions and cometary activity as old dust spirals away. The rate of replenishment and the rate of loss must be in approximate balance for the cloud structure to remain as observed, and measuring the structure precisely from an outside vantage would constrain this balance in ways that have implications for understanding the long-term evolution of the solar system. The zodiacal cloud is also a nuisance for certain astronomical observations. For missions seeking to detect the infrared emission or reflected light from planets around nearby stars, the zodiacal cloud of those star systems creates a foreground glow that competes with the planetary signal. By studying our own zodiacal cloud in detail from outside the disk, where its three-dimensional structure and its relationship to specific source populations can be characterized precisely, astronomers would gain insights into zodiacal cloud properties around other stars that would directly aid the interpretation of exoplanet observations. The zodiacal light from extrasolar systems is one of the primary concerns for next-generation planet-finding missions, and understanding our own system's zodiacal cloud in 3 dimensions from a vantage outside the plane is a crucial step toward addressing this challenge. Cosmic ray access at high ecliptic latitudes. Galactic cosmic rays are among the most energetic particles in the universe. Protons and heavier atomic nuclei accelerated to nearly the speed of light by supernova shock waves, pulsar magnetospheres, and other extreme astrophysical processes distributed throughout the Milky Way. They fill the galaxy roughly uniformly, streaming in from all directions, and they represent a significant radiation hazard for any mission beyond the protection of Earth's magnetic field. But the flux of cosmic rays reaching the inner solar system is not the same as the flux arriving from outside the heliosphere, because the Sun's magnetic field, carried outward by the solar wind, partially shields the inner solar system from the lowest energy cosmic rays through a process called solar modulation. Understanding how this modulation works at different latitudes within the heliosphere is one of the key scientific questions that a mission below the ecliptic would address. The heliospheric magnetic field that modulates cosmic rays is not uniform with latitude. At low latitudes near the ecliptic, the field is organized into the Parker spiral structure, winding outward from the Sun as the solar wind carries it while the Sun rotates. This spiral structure, combined with the presence of the current sheet and the stream interaction regions where fast and slow wind collide, creates a complex magnetic environment that scatters and deflects cosmic rays as they attempt to diffuse inward. At high latitudes above the polar coronal holes, the magnetic field is more organized, with field lines extending more nearly radially outward from the pole, and the modulation of cosmic rays is therefore different. The transition between these two regimes, from the complex turbulent low latitude field to the more organized high latitude field, is a region where the modulation efficiency changes, and where the cosmic ray access to the inner solar system is altered. Measuring the cosmic ray environment at different latitudes throughout the solar cycle provides critical information about how the heliosphere functions as a radiation shield, which has direct implications for human spaceflight planning. The dose received by astronauts in interplanetary space depends on the local cosmic ray flux, which varies with heliospheric latitude, solar cycle phase, and proximity to the current sheet. Current estimates of the cosmic ray environment at high ecliptic latitudes are based on extrapolation from in-ecliptic measurements combined with theoretical models, because very few direct measurements exist from high inclination vantages. The Ulysses mission provided the only comprehensive dataset of cosmic ray flux as a function of heliospheric latitude, measuring the environment from roughly 80 degrees inclination over 2 complete solar cycles. These measurements revealed significant differences in cosmic ray intensity between high and low latitude regions and between the two hemispheres, suggesting that the heliospheric modulation is more asymmetric and more latitude dependent than simple models had predicted. What made the Ulysses results particularly important was that they challenged the assumption that cosmic ray transport through the heliosphere could be described primarily by radial distance from the Sun. Prior to the mission, many models treated heliospheric shielding as largely symmetric, with latitude playing only a secondary role. Ulysses demonstrated that this picture was incomplete. During certain phases of the solar cycle, cosmic ray intensities at high heliographic latitudes differed substantially from those measured near the ecliptic, indicating that particles were finding pathways through the heliospheric magnetic field that existing transport models did not fully capture. The reason lies in the complexity of charged particle motion in magnetic fields. Cosmic rays do not travel in straight lines through the heliosphere. They scatter from magnetic irregularities, drift along gradients in magnetic field strength, and respond to the large-scale geometry of the heliospheric field itself. The current sheet, the wavy surface separating regions of opposite magnetic polarity, migrates dramatically over the course of the solar cycle. As it moves, it alters the preferred routes by which cosmic rays enter the inner solar system. During some magnetic configurations, particles can drift inward more efficiently through polar regions than through equatorial regions. During others, the opposite occurs. These effects produce latitude-dependent variations that can only be measured directly from high inclination trajectories. A modern mission operating below the ecliptic would have a substantial advantage over Ulysses, because the scientific instruments available today are vastly more capable. Particle detectors now possess higher energy resolution, greater directional sensitivity, and more sophisticated methods for identifying individual particle species. Instruments could separately measure protons, helium nuclei, heavier ions, and relativistic electrons across a wide range of energies, producing a far more detailed map of how different particle populations respond to heliospheric structure. Such measurements are particularly relevant because human spaceflight ambitions have expanded significantly since Ulysses flew. Planned missions to Mars, long-duration habitation in cislunar space, and eventual expeditions deeper into the solar system all face radiation exposure as one of their primary limiting factors. Galactic cosmic rays are difficult to shield against because their energies are so high that adding more shielding can sometimes create secondary particle cascades that increase the biological dose rather than reduce it. Understanding precisely how the heliosphere modulates these particles is therefore not merely a matter of astrophysics. It is a practical requirement for designing safe, deep space missions. A dedicated southward mission could also monitor how cosmic ray modulation changes as the solar cycle evolves. The Sun's magnetic field reverses polarity approximately every 11 years, producing a 22-year magnetic cycle that strongly influences particle transport. Continuous measurements from high southern latitudes throughout an entire cycle would allow scientists to test transport models with a precision that has never been possible. Such observations would improve forecasts of the radiation environment throughout the solar system and help determine how effective the heliosphere truly is as a shield against the galactic environment beyond. In that sense, a mission below the ecliptic would not simply be exploring an unfamiliar direction. It would be examining the structure of the protective magnetic bubble that makes life on Earth possible. The cosmic rays arriving from the galaxy carry information about supernovae, stellar explosions, and energetic events occurring thousands of light years away. The heliosphere determines how much of that information and how much of that radiation ultimately reaches the planets inside it. Understanding that interaction requires measurements from places we have almost never visited, the southern heliosphere remains one of those places. The interstellar boundary seen from below. At the outermost reach of the downward journey, many billions of kilometers from the Sun, lies the heliopause, the boundary where the Sun's outward flowing solar wind is balanced by the pressure of the local interstellar medium, the diffuse gas and dust that fills the space between stellar systems. The heliopause is the edge of the heliosphere, the Sun's bubble of influence, and crossing it means leaving the Sun's domain entirely and entering the interstellar medium proper. 2 spacecraft have crossed this boundary, both travelling in different directions within the ecliptic plane, and both transmitted measurements of the crossing back to Earth. No spacecraft has ever crossed the heliopause in the direction below the ecliptic, and the shape of the heliospheric boundary in this direction remains unknown, a blank region on the map of our local cosmic neighbourhood. The question of the heliosphere's shape is not settled. For decades, the standard model depicted the heliosphere as comet-like in shape, with a rounded nose on the side facing the direction of the Sun's motion through the interstellar medium and a long tail extending in the opposite direction. This model was supported by theoretical arguments about how a supersonic outflow interacts with a surrounding medium and, by analogy, with other stellar wind bubbles observed around other stars. But more recent analyses of data from Voyager 1 and Voyager 2, combined with observations from the IBEX spacecraft of energetic neutral atoms streaming inward from the boundary, have suggested a very different shape, more like a crescent or a deflated sphere with no extended tail, with the boundary relatively close to the Sun in all directions rather than extending much farther in the downwind direction. The 2 models make very different predictions for the boundary's location and structure, in directions other than those sampled by the Voyager spacecraft, including the direction below the ecliptic. Measuring the heliopause boundary in the downward direction would discriminate decisively between these models and provide the first direct data on the heliosphere's 3-dimensional shape. This is not simply a matter of cartographic completeness. The shape of the heliosphere determines how effectively it shields the inner solar system from galactic cosmic rays, how it modulates the flux of interstellar material that enters the solar system, and how it influences the conditions for life on Earth over geological timescales. As the solar system moves through the galaxy over millions of years, it encounters regions of interstellar medium with varying density and properties, and the heliosphere's response to these encounters determines whether the cosmic ray flux reaching Earth changes significantly, with potential implications for climate and biological evolution. A complete three-dimensional map of the heliosphere's current shape is the foundation for understanding how this response works. Since no spacecraft has ever sampled the heliopause from high southern heliographic latitudes, the uncertainty is not limited to the boundary's distance from the Sun. The physical structure of the boundary itself may vary significantly with latitude. Voyager 1 and Voyager 2 both observed that the heliopause is not a simple, static surface. It is a dynamic region shaped by the interaction between the solar wind, the interstellar magnetic field, and the flow of interstellar plasma around the heliosphere. Measurements from a downward trajectory would reveal whether the southern heliopause possesses the same thickness, turbulence, and magnetic structure observed at the Voyager crossing points, or whether entirely different conditions prevail there. One of the most important measurements would be the behavior of the interstellar magnetic field as it drapes around the heliosphere. As the Sun moves through the local interstellar medium at roughly 26 kilometers per second, the interstellar magnetic field cannot pass directly through the heliosphere. Instead, the field lines are compressed, bent, and redirected around the heliospheric boundary. The geometry of this interaction influences the penetration of charged particles into the solar system and may play a significant role in determining the overall shape of the heliosphere itself. Direct measurements from a southern crossing would provide a second independent perspective on this magnetic interaction, allowing scientists to reconstruct the three-dimensional structure of the boundary for the first time. The downward direction is also scientifically valuable because it samples a region of interstellar space that may differ from the environments encountered by the Voyager spacecraft. The Sun is currently moving through a structure known as the local interstellar cloud, a tenuous region of gas approximately 30 light-years across, embedded within a larger cavity called the local bubble. The density, temperature, ionization state, and magnetic properties of this cloud are not perfectly uniform. A spacecraft leaving the heliosphere in a significantly different direction would probe a different portion of the cloud and test whether the local interstellar environment varies on scales of tens or hundreds of astronomical units. Such measurements would have implications extending well beyond heliophysics. Every star with a stellar wind creates an astrosphere analogous to the Sun's heliosphere. Yet because humanity can directly study only one example from the inside, our understanding of how astrospheres interact with the interstellar medium remains limited. A complete three-dimensional characterization of our own heliosphere would provide the benchmark against which observations of stellar systems around other stars are interpreted. It would help astronomers understand how effectively other stars shield their planets from galactic radiation, and how those shielding properties evolve as stars move through different galactic environments. In that sense, a mission crossing the heliopause below the ecliptic would not merely be exploring a neglected direction, it would be transforming the heliosphere from a boundary sampled at two isolated points into a genuinely mapped structure. The edge of the Sun's influence is one of the largest physical features associated with our solar system, yet much of its shape remains inferred rather than observed. Travelling downward would allow humanity, for the first time, to see whether the bubble surrounding our star truly looks the way our models say it should, or whether another surprise is waiting at the edge of everything we call home. Why the view from below changes everything we think we know. Every observation of the solar system ever made from Earth or from any spacecraft has been made from within the plane of the ecliptic, or within a few tens of degrees of it. This is not a small constraint. It means that the entire scientific understanding of the solar system, built up over centuries of increasingly sophisticated observation, is an understanding built from a single fixed perspective, as if a geographer had tried to map a continent by walking only along one latitude line and never travelling north or south to see how the terrain varied with distance from that line. The solar system's vertical dimension, the structure that exists above and below the plane, is the dimension that has been least observed, least characterized, and least understood. The specific objects and phenomena that lie in the downward direction, the Sun's south pole, the southern polar coronal hole and the fast wind it produces, the structure of the heliospheric current sheet seen in plan view, the zodiacal dust disk seen from outside, the cosmic ray environment at southern heliospheric latitudes, and the shape of the heliopause in the downward direction are not minor details of a system otherwise well understood. Each of them is connected to fundamental questions about how the Sun functions, how the heliosphere protects and exposes the inner solar system to the galaxy beyond, and how the solar system as a whole exists as a three-dimensional object embedded in the larger structure of the galaxy. These questions cannot be addressed from inside the plane. They require the view from below. The technical path to obtaining that view exists. The perihelion burn strategy, the Venus gravity assist strategy used by solar orbiter, the solar sail approach, and the combination of these methods all represent viable trajectories to high ecliptic inclinations that could be implemented with foreseeable technology. No single approach is without challenges. The perihelion burn requires thermal engineering at the limit of what has been demonstrated. The gravity assist approach requires many years of patient flyby accumulation, and the solar sail approach requires lightweight deployment of large structures that have been demonstrated only at small scales. But none of these challenges is a fundamental physical barrier. They are engineering problems with identifiable solutions. The missions have been designed on paper many times over. They have not been built, not because they are impossible, but because they have not yet been made a priority. What waits below the floor of the solar system is not emptiness. It is the bottom half of our own star, the source of the fastest and most structured of the solar winds, the clean view of a magnetic reversal process that governs decades-long patterns of solar activity, the perspective from which the heliosphere's true shape becomes measurable, and the zodiacal cloud reveals its three-dimensional architecture for the first time. It is the direction from which the universe, beyond the contaminating foreground of our own solar system's disk, appears in its least obscured form. The view from below is not merely a different angle on familiar objects. It is a genuinely new territory in the exploration of the system we call home, and it is waiting. The scientific value of such a mission extends beyond heliophysics and into planetary science itself. Viewed from Earth, the planetary system appears as a thin line because the major planets form from a rotating disk of gas and dust and therefore orbit in nearly the same plane. But that flat appearance can create the misleading impression that the solar system itself is fundamentally flat. In reality, every major component of the system possesses a vertical structure that remains only partially measured. The asteroid belt extends above and below the ecliptic. The Kuiper belt contains populations of objects on significantly inclined orbits. Long-period comets arrive from all directions, tracing trajectories that suggest a vast spherical reservoir surrounding the planetary region. A high-inclination mission would provide a perspective from which these structures could be mapped with far greater precision, revealing how material is distributed above and below the plane in ways that are difficult to reconstruct from observations made within it. The same perspective would transform our understanding of the Sun's relationship to the galaxy. The solar system is not stationary. It moves through the Milky Way at roughly 230 kilometers per second, while oscillating above and below the galactic plane over tens of millions of years. The interaction between the heliosphere and the surrounding interstellar medium is therefore not constant, but evolves as the solar system encounters regions of differing density, magnetic field strength, and particle composition. Understanding how the heliosphere responds to those changes requires first understanding its present three-dimensional structure. Without measurements from high southern latitudes, that structure remains incompletely constrained. There is also an important philosophical dimension to the scientific argument. Exploration has historically proceeded outward because outward is where the unknown was easiest to see. The oceans beyond the horizon, the planets beyond Earth, the stars beyond the planets. But sometimes the most significant unknown is not farther away. Sometimes it is simply a direction that has been neglected. The southern heliosphere represents one of the few remaining regions of the solar system that has never been systematically explored, despite being part of our immediate cosmic environment. Future generations will almost certainly send spacecraft there. The scientific questions are too fundamental and the observational gaps too large to remain unanswered indefinitely. Whether through solar sails, advanced gravity assist architectures, nuclear electric propulsion, or technologies not yet invented, humanity will eventually obtain the view from below. When that happens, the resulting discoveries may appear obvious in retrospect, just as the first images of the far side of the Moon or the first close-up views of the outer planets now seem inevitable. But before those missions flew, those worlds were largely matters of inference and imagination. The solar system beneath the ecliptic remains in a similar state today, not completely unknown, but known primarily through models and indirect evidence. The view exists. The physics allows us to reach it. The only missing ingredient is the decision to go. The southern heliosphere, a region no instrument has mapped. Everything known about the heliosphere as a physical structure has been assembled from measurements made within a narrow band of heliocentric latitude. The great majority of all spacecraft that have ever operated in interplanetary space have stayed within roughly 30 degrees of the ecliptic plane, and most have stayed within 10 degrees or less. The heliosphere extends above and below this band for a full 90 degrees in each direction, from the ecliptic all the way to the solar poles. And the properties of this enormous volume of space are known primarily from inference and from theoretical models rather than from direct measurement. The southern heliosphere specifically, the hemisphere below the ecliptic plane, has been sampled by exactly one spacecraft across the entire history of space exploration, the Ulysses mission, which spent portions of 2 complete solar cycles at high southern latitudes while travelling on its inclined orbit around the Sun. Ulysses reached a maximum southern ecliptic latitude of approximately 80 degrees during its first southern polar pass in 1994, and repeated this pass during its second orbit in 2000. The data returned from these passes established the basic character of the southern high-latitude heliosphere. Fast, smooth solar wind emanating from the southern polar coronal hole at low solar activity. A more complex structured wind at higher solar activity when the coronal hole shrinks and active regions at lower latitudes produce variable outflow. Cosmic ray intensities different from those measured at ecliptic latitudes, and a magnetic field whose properties at high southern latitudes differed from what simple models predicted in ways that took years of analysis to understand. These are genuinely significant scientific results. They also represent the sum total of direct observational knowledge of the southern heliosphere accumulated over brief passes by a single spacecraft now silent for over a decade. The southern heliosphere is not simply a mirror image of the northern heliosphere. The Sun's magnetic field is not perfectly symmetric between its 2 hemispheres, and this asymmetry expresses itself in the properties of the solar wind, the cosmic ray environment, and the structure of the heliospheric magnetic field at different latitudes. During some phases of the solar cycle, the north and south polar coronal holes differ significantly in size, shape, and field strength. The heliospheric current sheet is often tilted asymmetrically, spending more time north or south of the ecliptic, depending on the phase of the cycle and the detailed configuration of active regions at lower latitudes. These asymmetries mean that measurements in the southern heliosphere are not simply redundant with northern hemisphere data, but encode independent information about the global state of the solar magnetic system. Mapping the southern heliosphere systematically, measuring the solar wind, the magnetic field, the cosmic ray flux, and the plasma properties as continuous functions of latitude and solar distance over a full solar cycle is one of the primary scientific objectives that motivates the development of polar solar mission concepts. Such a map would allow direct comparison of the northern and southern hemispheres, enabling tests of solar magnetic field models that currently must be compared only with ecliptic latitude data. It would reveal whether the asymmetries observed in the solar magnetic field surface maps propagate coherently into the heliosphere or are smoothed out by the wind expansion. It would provide the ground truth needed to validate the theoretical framework used to predict space weather conditions at Earth, which depends on models of how the Sun's polar field configuration affects the overall structure of the solar wind. Every one of these scientific products requires sustained measurement over years in the southern heliosphere, not a brief high-latitude pass by a fast-moving spacecraft. The scientific need exists. The observation has not been made. A particularly important aspect of such observations would be the study of the Sun's polar magnetic fields during the periods surrounding solar minimum. The polar fields are not merely another component of the Sun's magnetic system. They are believed to be the primary reservoir of magnetic flux that seeds the next solar cycle. Measurements of the strength and structure of these fields are therefore central to predicting the future evolution of solar activity. Yet from Earth's vantage point, the poles are observed at a severe angle, introducing geometric uncertainties that limit the precision of magnetic field reconstructions. A spacecraft operating deep in the southern heliosphere would observe the South Pole directly, providing magnetic field measurements that could significantly improve solar cycle prediction models. The benefits would extend beyond solar physics into practical space weather forecasting. Coronal mass ejections, high-speed solar wind streams, and energetic particle events all propagate through a heliosphere whose large-scale structure is shaped by the Sun's global magnetic field. Errors in understanding that structure translate directly into errors in predicting how solar disturbances travel through interplanetary space. As human activity expands beyond Earth orbit, with permanent infrastructure in cislunar space, missions to Mars, and increasingly complex satellite networks, the ability to forecast space weather becomes a matter of operational necessity rather than purely scientific curiosity. Better measurements of the southern heliosphere would improve the physical models on which these forecasts depend. There is also the question of long-term heliospheric evolution. The solar wind does not expand into a static environment. It interacts continuously with the local interstellar medium, and the nature of that interaction depends on the global distribution of solar wind pressure emerging from all latitudes. Because the polar regions contribute a substantial fraction of the heliosphere's total momentum and magnetic flux, uncertainties in the properties of the southern high-latitude wind propagate into uncertainties in models of the heliosphere as a whole. Understanding the distant boundaries of the Sun's influence therefore begins with understanding the regions near the poles where much of that influence originates. Perhaps most striking is how little additional exploration would be required to transform this field. The southern heliosphere is not located hundreds of light years away or hidden behind exotic physical barriers. It is part of the Sun's immediate environment. The gap in knowledge exists not because the region is inaccessible, but because spacecraft trajectories have historically been optimized for planetary encounters that occur near the ecliptic plane. As a consequence, one of the largest volumes of space directly associated with our own star remains only sparsely sampled. For a civilization that has sent probes beyond the heliopause, landed on comets, and photographed every major planet, this is an unusual situation. Entire disciplines of heliophysics still rely on extrapolations into regions where direct measurements are scarce. The southern heliosphere remains one of the last places in our own solar system where a single dedicated mission could fundamentally change the observational foundation of an entire field. It is not unexplored because it lacks importance. It is unexplored because we have spent almost all of our history looking sideways rather than down. What interstellar dust flowing into the solar system tells us about our neighborhood? The solar system is not isolated from its galactic environment. The interstellar medium that surrounds the heliosphere is not static, and its contents do not stop at the heliopause. Neutral interstellar atoms, those without electric charge and therefore unaffected by the heliospheric magnetic field, can penetrate deep into the solar system, and so can interstellar dust grains too large and heavy to be swept away by radiation pressure. Detecting and characterizing this interstellar material as it flows through the inner solar system provides a direct sample of the interstellar medium surrounding the Sun, a sample that would otherwise require travelling to the heliopause and beyond to obtain. This interstellar material arrives preferentially from the direction of the Sun's motion through the local interstellar cloud, which is roughly in the ecliptic plane, but its three-dimensional distribution and the subtle variations in its properties with latitude can reveal information about the structure of the interstellar medium that cannot be obtained any other way. Interstellar dust was first detected flowing through the inner solar system by the dust detectors on the Ulysses spacecraft during its high-latitude passes. The detection was significant because it demonstrated that interstellar grains penetrate deep inside the heliosphere and that they have measurable properties distinguishable from local solar system dust. The interstellar grains detected by Ulysses were larger on average than expected, based on models of the interstellar grain size distribution derived from astronomical observations of distant stars. This discrepancy remains incompletely explained and suggests that the filtering of interstellar grains by the heliospheric magnetic field is size-dependent in ways that models have not fully captured. The flow direction and velocity of interstellar grains entering the solar system encodes information about the relative motion between the Sun and the local interstellar cloud, the same motion that shapes the heliosphere into its asymmetric form, with a compressed nose and an extended wake. By measuring the grain properties at different heliocentric latitudes, the three-dimensional flow pattern of interstellar material into the solar system can be mapped. This map would constrain models of how the heliosphere interacts with the surrounding medium, and specifically how different particle sizes and charges are filtered or deflected by the heliopause and by the heliospheric magnetic field during their inward journey. The differences between grain properties at high ecliptic latitudes compared to low ecliptic latitudes would reflect the latitude dependence of the filtration process, which in turn depends on the heliosphere's shape and field structure in the polar regions. Beyond the practical scientific objectives, there is something philosophically significant about measuring interstellar material inside our own solar system. The Sun formed from a molecular cloud that contained material from many previous generations of stars, supernovae that scattered their processed heavy elements into space before the solar nebula collapsed. The interstellar grains now entering the solar system from the surrounding medium are cousins of the material from which the solar system itself was built, processed through different astrophysical environments, but originating from the same broad category of stellar nucleosynthesis. Analysing their composition is in a sense reading a letter from the broader galaxy, a sample of the material context in which the solar system is embedded, delivered to our doorstep by the flow of interstellar wind through the heliosphere. A mission operating below the ecliptic would provide an especially valuable perspective on this interstellar flow because it would observe the incoming material from a vantage point largely unavailable to previous spacecraft. Nearly all measurements of interstellar dust, neutral hydrogen, neutral helium, and related populations have been obtained from trajectories that remained relatively close to the solar system's central plane. While these measurements have revealed the existence and general properties of the inflowing material, they offer only a limited view of its three-dimensional structure. A spacecraft travelling to high southern heliographic latitudes could measure how the density, velocity distribution and composition of interstellar particles vary with latitude, providing a much more complete picture of how the heliosphere interacts with the surrounding galactic environment. One particularly important target would be neutral helium. Unlike hydrogen, which is strongly affected by interactions with solar ultraviolet radiation and charge exchange processes, helium penetrates the heliosphere relatively unchanged. Measurements of neutral helium therefore provide one of the most reliable probes of the local interstellar medium. By tracking the flow of helium across a wide range of latitudes, scientists could refine estimates of the Sun's motion relative to the surrounding cloud and improve models of the pressure balance that defines the heliopause. Even small improvements in these measurements would have consequences for understanding the overall geometry of the heliosphere and its effectiveness as a shield against galactic cosmic rays. High-latitude observations would also help answer a long-standing question regarding the interaction between interstellar dust and the solar magnetic field. Charged dust grains experience electromagnetic forces as they move through the heliosphere, causing their trajectories to deviate from purely gravitational paths. The extent of this deviation depends on grain size, charge, and the changing configuration of the solar magnetic field over the solar cycle. Current models predict latitude-dependent effects that have never been tested comprehensively because the necessary observations do not yet exist. A polar mission could provide the first direct measurements capable of determining whether these predictions are correct. Such observations would connect local heliophysics with broader astrophysical questions. The composition of interstellar dust grains contains information about the environments in which they formed, including the outflows of dying stars, supernova explosions, and dense molecular clouds where new stars are born. Every grain entering the heliosphere carries a record of processes occurring elsewhere in the galaxy. By studying these particles directly, rather than inferring their properties from distant astronomical observations, researchers gain access to a level of detail that is otherwise impossible to obtain. In this sense, a journey below the solar system is not only an exploration of the Sun's southern hemisphere or the structure of the heliosphere. It is also an exploration of the boundary between our planetary system and the galaxy beyond. The particles drifting through that boundary are among the few physical samples of interstellar space that naturally reach us. Mapping their behavior from a high-latitude vantage would reveal how the solar system exchanges matter with its surroundings and would transform our understanding of the thin but consequential frontier separating the Sun's domain from the wider Milky Way. The view of the galaxy. With the solar system's contamination removed. From any vantage point inside the ecliptic plane, every observation of the universe beyond the solar system is made through a foreground of zodiacal dust, scattered sunlight, and the faint thermal emission of the dust grains that fill the inner solar system. This foreground is not catastrophically bright, but it is ubiquitous and it degrades the quality of observations that depend on detecting very faint signals, particularly observations in the infrared, where the thermal emission of room temperature or slightly warmer dust is most significant. The foreground is minimized in directions perpendicular to the ecliptic, above and below the plane, because the dust is concentrated in the plane and thins rapidly with latitude. A spacecraft below the ecliptic, looking outward into the universe in the downward direction, would be looking through dramatically less zodiacal foreground than any telescope on Earth or in Earth orbit. This matters most for two categories of astronomical observation. The first is the search for and characterization of exoplanets using direct imaging, where the goal is to detect the faint reflected starlight or thermal emission from a planet orbiting a nearby star against the background of the star's own much brighter light and the diffuse foreground of zodiacal and extrasolar zodiacal emission. The technical challenge of direct imaging exoplanet missions is dominated by the need to suppress the foreground while preserving the planetary signal. And the zodiacal foreground from our own solar system is one of the most important noise sources. Observing from below the ecliptic plane would reduce this foreground by a factor that depends on the ecliptic latitude achieved, with the improvement becoming substantial above roughly 45 degrees of latitude and dramatic at latitudes approaching 90 degrees. An exoplanet imaging telescope operating from a polar solar orbit would have access to a significantly cleaner sky than any telescope confined to the ecliptic, and this clean sky translates directly into shorter integration times required to detect a given planetary signal and smaller telescope aperture needed to achieve a given detection sensitivity. The second category, where the cleaner southern sky would provide significant benefit, is the measurement of the cosmic microwave background, the faint relic radiation from the early universe that fills the sky uniformly at temperatures of approximately 2.7 Kelvin. The cosmic microwave background carries information about the density fluctuations in the early universe that seeded all subsequent structure formation, and its precise measurement is one of the most powerful tools available for testing cosmological models and determining the universe's composition and evolution. The primary obstacle to more precise measurement is the removal of foreground contributions, including emission from our own galaxy's dust and free electrons, as well as emission from the zodiacal dust in the solar system. The galactic foreground must be subtracted regardless of where the telescope is positioned, but the zodiacal foreground is reduced below the ecliptic. A cosmic microwave background experiment conducted from high ecliptic latitude would have a lower zodiacal foreground contribution, enabling cleaner measurements of the faint temperature fluctuations in the cosmological signal that are most sensitive to fundamental cosmological parameters. The southern galactic sky, as seen from below the ecliptic, also includes some of the most scientifically interesting regions of the Milky Way, viewed from a cleaner perspective. The galactic center lies at ecliptic latitude roughly -6 degrees, very close to the ecliptic, and its observation benefits primarily from reduced solar system foreground rather than from any geometric advantage of a high-latitude vantage. But the Magellanic Clouds, the two satellite galaxies of the Milky Way visible from the southern hemisphere of Earth and providing irreplaceable targets for stellar physics, distance measurement, and galaxy evolution studies, lie at high southern ecliptic latitudes where the zodiacal foreground is significantly reduced. A telescope operating from below the ecliptic plane would observe the Magellanic Clouds against a cleaner background than any Earth-based or Earth orbit telescope can achieve, potentially revealing faint diffuse emission structures in and around these galaxies that are currently hidden beneath the zodiacal glow. The advantages extend beyond specific astronomical targets. A telescope positioned far below the ecliptic would function as a pathfinder for a fundamentally different approach to observational astronomy, placing observatories where the solar system itself contributes the least possible interference to measurements. Modern astronomy increasingly confronts limits imposed not by detector technology or mirror size, but by foreground contamination. As instruments become more sensitive, the brightness of the foreground becomes the dominant obstacle. Reducing that foreground at the source by changing the observing location rather than attempting increasingly sophisticated subtraction techniques is often the more effective solution. There is also a unique scientific value in directly measuring the zodiacal cloud from the outside. Every current model of the cloud's three-dimensional structure is reconstructed from observations made within it, a situation analogous to attempting to map a forest while standing among the trees. A high-latitude observatory could image the dust disk in its entirety, determining its thickness, asymmetries, density variations, and long-term evolution with unprecedented precision. Such measurements would improve not only solar system science, but also the interpretation of debris disk, or confined, observed around other stars, which are often studied as analogues of our own planetary system. From below the ecliptic, the universe would not simply appear different. It would appear cleaner, allowing astronomers to separate local structure from cosmic structure with a clarity that has never before been available from within the solar system's crowded central plane. Gravity waves. From below, what the ecliptic's floor hides from detectors. Gravitational wave astronomy has transformed our understanding of the universe since the first direct detection of gravitational waves by the LIGO detectors in 2015. Merging black holes, colliding neutron stars, and other catastrophic astrophysical events produce ripples in space-time that propagate at the speed of light and can be detected by measuring the tiny changes in the distance between widely separated test masses. The LIGO and Virgo ground-based detectors have demonstrated that gravitational wave astronomy is not merely possible, but enormously productive, opening an entirely new observational window on the universe's most violent events. But ground-based detectors are limited to frequencies above roughly 10 Hz by the irreducible noise floor of seismic activity on Earth. The most interesting gravitational wave sources in the millihertz frequency range, including supermassive black hole mergers, compact binary systems in their early in-spiral phases, and the gravitational wave background produced by the universe's entire population of merging compact objects, require detectors with arm lengths far greater than can be built on Earth. The proposed LISA mission, the Laser Interferometer Space Antenna, is a European Space Agency-led project to deploy 3 spacecraft in a roughly equilateral triangle formation, each separated from the others by approximately 2.5 million kilometers, flying in a heliocentric orbit slightly behind Earth. The separations between LISA's 3 spacecraft act as the interferometer arms, and gravitational waves passing through the detector volume would produce tiny changes in these separations measurable by comparing laser signals exchanged among the 3 spacecraft. LISA is designed to operate in the millihertz frequency band and would be sensitive to a broad population of astrophysical sources, including supermassive black hole mergers at cosmological distances, the gravitational wave background from the thousands of compact binary systems in our own galaxy, and potentially exotic sources such as gravitational waves from the early universe. LISA's planned orbital configuration, following Earth's orbit around the Sun, with the detector plane tilted approximately 60 degrees relative to the ecliptic, represents a compromise between the scientific requirement for a stable detector orientation, the practical requirement for continuous solar power, and the engineering constraints of the mission. This configuration keeps the 3 spacecraft within a manageable distance of Earth for communication and places the detector in a relatively quiet gravitational environment. But the detector's sensitivity pattern, the set of sky directions from which it can most efficiently detect gravitational waves, is partially shaped by the ecliptic geometry because the orbital configuration references the ecliptic plane. A gravitational wave detector operating in a polar heliocentric orbit, oriented perpendicular to the ecliptic, would have a fundamentally different sensitivity pattern that is complementary to an ecliptic plane detector. The combination of an ecliptic plane detector like LISA with a polar orbit detector would provide full sky gravitational wave coverage with minimal gaps in sensitivity for any source direction. For gravitational wave sources distributed uniformly across the sky, which is the expected distribution for cosmological events, the combined network would provide sky localization significantly better than either detector alone. For sources with known positions, such as the compact binary systems in our galaxy, the ability to observe from 2 orthogonal orientations would eliminate the directional ambiguities that affect any single orientation detector and would dramatically improve parameter estimation for the source properties. The gravitational wave background from our own galaxy, produced by the approximately 25 million compact binary systems estimated to exist in the Milky Way, would be particularly well characterized by a polar orbit gravitational wave detector. The galactic binary background appears in the LISA frequency band as a confusion-limited foreground source whose angular distribution traces the disk of the Milky Way. A polar orbit detector would observe this background from a direction perpendicular to the galactic disk, providing a view of its angular distribution that would complement the in-plane view available from LISA. Combining the 2 perspectives would allow the 3-dimensional distribution of compact binaries in the galaxy to be mapped in a way that neither detector alone could achieve. The benefits extend beyond improved source localization and population studies. One of the most powerful techniques in gravitational wave astronomy is the use of multiple detectors to distinguish genuine gravitational wave signals from instrumental noise. A signal detected simultaneously by 2 detectors with different orientations and different orbital locations can be verified with far greater confidence than a signal detected by a single observatory. This principle has been fundamental to the success of ground-based gravitational wave astronomy, where the combined observations of LIGO, Virgo, and CAGRA provide much stronger scientific constraints than any detector operating alone. A space-based polar detector would extend this principle into the millihertz regime, creating a true interplanetary gravitational wave network. Such a network would be particularly valuable for studying supermassive black hole mergers. These events can remain detectable for months or even years before the final coalescence, allowing their positions on the sky to be refined gradually as more data are collected. Observations from two detectors viewing the source from substantially different geometries would reduce uncertainties in distance, mass, spin, and orbital orientation. This improved precision would allow astronomers to identify the host galaxies of merging black holes more reliably, linking gravitational wave observations directly to electromagnetic observations and enabling a deeper understanding of galaxy evolution across cosmic history. A polar orbit detector would also provide a unique opportunity to search for anisotropies in the stochastic gravitational wave background. If the background contains directional structure arising from the large-scale distribution of galaxies, clusters, or relic signals from processes in the early universe, observations from multiple detector orientations would help separate these genuine cosmological features from instrumental effects. The result would be a three-dimensional map of the gravitational wave sky, analogous to the maps of the cosmic microwave background that transformed cosmology in the late 20th century. In this sense, a gravitational wave observatory operating far above or below the ecliptic would not merely duplicate the capabilities of LISA, it would add an entirely new geometric perspective, turning gravitational wave astronomy from a single-view observation into a stereoscopic exploration of the dynamic universe. The Ulysses legacy and what it left unanswered. The Ulysses mission remains the only spacecraft to have travelled to high ecliptic latitudes and directly measured the heliospheric environment above and below the plane of the planets. Launched in October 1990 and operating until June 2009, a mission lifetime of nearly 19 years, Ulysses completed 3 full orbits of the Sun on its inclined trajectory, each orbit bringing it to high southern and northern latitudes in a sequence that spanned more than 1.5 full solar cycles. The data it returned fundamentally changed scientific understanding of the three-dimensional heliosphere and earned it a place among the most scientifically productive missions in the history of solar system exploration. The mission's trajectory was itself an engineering achievement of the first order. There was no direct route from Earth to a high-inclination solar orbit that could be achieved with available propulsion. Instead, Ulysses was launched toward Jupiter, reaching the giant planet in February 1992. The Jupiter Gravity Assist, carefully designed to swing the spacecraft into a trajectory sharply inclined to the ecliptic, redirected Ulysses onto its polar orbit without consuming any spacecraft propellant for the inclination change. The maneuver bent the spacecraft's trajectory by 83 degrees relative to the ecliptic in a single Jupiter flyby, an achievement that no rocket burn could have accomplished with any feasible fuel load. Ulysses then travelled inward and outward around the Sun on its inclined orbit, reaching southern heliocentric latitudes as high as 80 degrees during its polar passes. The primary scientific findings from Ulysses can be organised around several themes that defined what was previously unknown about the three-dimensional heliosphere. The confirmation of the bimodal solar wind, with fast wind from polar coronal holes and slow wind from equatorial regions, was the mission's most cited result. Before Ulysses, the polar origin of the fast wind was strongly suspected from theoretical arguments and from remote sensing observations of the corona, but it had never been directly confirmed by in situ measurements at high heliocentric latitudes. Ulysses particle detectors measured the wind speed, density, temperature and composition continuously as the spacecraft climbed to higher latitudes, and the transition from slow to fast wind that occurred as the spacecraft left the equatorial streamer belt and entered the high-latitude fast wind regime was unambiguous. The fast wind was not only faster, but also more uniform, less variable, and compositionally distinct from the equatorial wind in ways that directly reflected the different magnetic structures from which the two wind types originated. The unexpected uniformity of the heliospheric magnetic field at large distances from the Sun was a second major finding. At high heliocentric latitudes and large distances from the Sun, the radial component of the heliospheric magnetic field was found to be approximately equal in all directions, regardless of latitude. This violated the expectation, based on the Parker spiral model of the heliospheric field, that the radial field component would be stronger at the poles, where the field emerged more directly from the polar coronal holes. The surprising uniformity required theoretical explanation and led to revised models of how the solar wind carries magnetic flux outward and how the field becomes isotropic at large distances. The explanation ultimately involved the way the solar wind expansion redistributes field lines that emerge from different solar latitudes as they propagate outward, smoothing out the initial latitude dependence. This understanding has important implications for models of cosmic ray propagation through the heliosphere, because the distribution of cosmic rays across heliocentric latitudes depends on the structure of the magnetic field they propagate through. What Ulysses left unanswered is in some respects as important as what it established. The mission carried no camera, no imaging instrument capable of photographing the Sun's polar regions from its high-latitude vantage. Every scientific result from Ulysses was derived from in situ particle and field measurements, extremely valuable but unable to connect directly to the visual structures visible in the solar atmosphere. The mission was also a fast mover, spending relatively little time at its maximum latitudes during each polar pass before its orbit swept it back toward lower latitudes. A spacecraft truly hovering above a solar pole, making continuous observations of the polar region over years rather than weeks, would accumulate a dataset orders of magnitude richer than anything Ulysses could provide. The Ulysses legacy is the foundation. The structure that should be built on it has not yet been started. What a sustained polar solar observatory would reveal over one full solar cycle. The solar magnetic cycle, with its approximately 11-year period from one minimum of activity to the next, represents the fundamental clock of solar behavior. The sunspot cycle, the corona's seasonal transformation from the streamlined quiet structure of solar minimum to the complex disordered structure of solar maximum, the reversal of the global magnetic field polarity that occurs near each maximum, the ebb and flow of space weather activity at Earth, all of these are manifestations of a single underlying dynamo process that operates deep inside the Sun, and whose ultimate expression is visible at the solar poles, where the accumulated magnetic flux of each cycle reverses the polarity of the polar field. Observing one complete solar cycle from a sustained polar vantage point would provide a data set that no other observational strategy can replicate, and that would transform understanding of the solar dynamo at its most fundamental level. The key measurements that a polar solar observatory would make continuously over an 11-year cycle are the spatial structure and temporal evolution of the polar coronal holes as they grow from their maximum extent at solar minimum, shrink towards solar maximum, disappear entirely during the polar field reversal, and then re-establish with opposite polarity as the new cycle begins. The properties of the fast solar wind as a function of its position within the polar coronal hole, specifically measuring how the wind speed and density vary from the center of the hole to its boundaries, and how these properties change as the hole evolves through the cycle. The detailed structure and temporal evolution of the polar magnetic field as measured by a magnetograph capable of resolving the fine-scale magnetic features that characterize the polar region, and the distribution and dynamics of polar plumes, the ray-like structures that extend outward from the polar coronal holes along open magnetic field lines and that are thought to contribute to the fast wind structure. The polar field reversal itself, the event at the heart of the solar cycle's magnetic reset, has never been observed continuously and at high resolution from a polar vantage. From Earth's perspective inside the ecliptic, the polar field is always seen foreshortened, and the small-scale structures involved in the reversal are compressed below the resolution limit of even the best observations. The reversal appears in ground-based and space-based magnetograph data as a gradual reduction in the net polar field strength, followed by a period of mixed or absent polar field, followed by the establishment of a new polar field with opposite polarity. But the detailed spatial pattern of how this reversal proceeds, whether it happens uniformly across the pole or in patches that gradually coalesce, how it relates to the arrival of magnetic flux from lower latitudes carried poleward by meridional flows, and how the transition from the old polarity to the new one is organized in both time and space. These are all questions that cannot be answered from the foreshortened perspective available from inside the ecliptic. A polar solar observatory directly above the south pole of the Sun, during a field reversal, would observe the event from the only vantage that allows the full two-dimensional spatial structure of the polar field to be seen without foreshortening. The magnetograph would map the field polarity across the polar cap in genuine spatial coordinates, revealing whether the reversal proceeds as a uniform retreat of the old polarity followed by a uniform advance of the new polarity, or whether it involves complex spatial patterns of mixed polarity that evolve in specific ways. This spatial information would be directly usable as input to dynamo models that seek to reproduce the reversal process from first principles. Currently, these models are calibrated against the one-dimensional time series of average polar field strength that ground-based synoptic programs provide, because that is the only data available. Calibrating against the actual two-dimensional spatial evolution of the polar field during reversal would be a qualitatively different kind of constraint on the models. The implications of a better constrained solar dynamo model extend beyond the academic. The strength of the next solar cycle can be predicted more reliably from the strength of the polar field at the previous minimum. But the relationship is imprecise because the polar field measurement from inside the ecliptic is itself imprecise. A more accurate measurement of the true polar field strength from a polar vantage would translate directly into more accurate predictions of the next cycle's intensity, with real consequences for space weather preparedness, for satellite hardening decisions, and for the planning of human space missions that must account for the radiation environment during different phases of the solar cycle. Below the galactic plane, what lies in the larger vertical direction? The direction directly below the solar system has a meaning at two scales. At the scale of the solar system itself, it means perpendicular to the ecliptic plane and toward the south ecliptic pole. But the solar system itself sits within the disk of the Milky Way galaxy, and the galactic disk has its own plane, its own vertical direction, its own above and below. The ecliptic plane and the galactic plane are not the same plane. They are tilted relative to each other by approximately 60 degrees. This means that the direction directly below the solar system in an ecliptic sense, the south ecliptic pole, is not the same as the direction directly below the Milky Way's disk in a galactic sense. A spacecraft travelling in the direction directly below us in ecliptic terms is actually travelling at roughly 60 degrees from the direction perpendicular to the galactic plane, at a significant angle but not directly toward the galactic south pole. The distinction matters because the structures encountered on a journey in the south ecliptic direction change character as the distance scale increases beyond the heliosphere. Within the solar system, the relevant geometry is the ecliptic plane and the solar equatorial plane. Between the solar system and the nearest stars, the geometry of the local interstellar medium is partly aligned with the galactic plane and partly structured by local features like the local bubble. At greater distances, the galactic plane becomes the dominant organizing structure. A spacecraft travelling south ecliptically would, at very large distances from the solar system, be travelling in a direction that is not perpendicular to the galactic disk, but at an angle to it, eventually exiting the galactic disk on one side, rather than through the pole. The local bubble, the roughly 300 light-year diameter cavity in the interstellar medium that surrounds the solar system, was excavated by a series of supernova explosions over the past 10 to 20 million years. The bubble is not perfectly spherical. It has a more complex shape with different extents in different directions, and one of the largest openings in its boundary, sometimes called the chimney, extends in the direction of the galactic south pole, aligned more with the galactic vertical than with the ecliptic vertical. A spacecraft travelling in the south ecliptic direction would be travelling at roughly 60 degrees from this chimney direction, through a part of the local bubble's boundary that is less open than the galactic south polar chimney, but still part of the low-density cavity that surrounds the solar system. Beyond the local bubble, the interstellar medium becomes denser and more structured, reflecting the distribution of gas and dust in the Milky Way's disk. The density of interstellar material drops off with distance above and below the galactic plane, and a spacecraft travelling at 60 degrees to the galactic vertical would be moving both away from the galactic plane and along it simultaneously, traversing a region of progressively lower average density as it climbs away from the dense mid-plane. The most interesting structures in the interstellar medium at these scales are the molecular clouds, dense concentrations of cold gas and dust where new stars form, and the supernova remnants that have displaced gas from the mid-plane and created the bubble structure that surrounds the solar system. The distribution of these structures in the southern ecliptic direction reflects both the galactic geometry and the specific history of stellar evolution in the solar neighbourhood over the past few tens of millions of years. At the larger scales, a spacecraft travelling in the south ecliptic direction would eventually be looking back toward the Milky Way from outside its disk, viewing the galaxy from a perspective that no instrument has ever occupied. The Milky Way, seen from a point 60 degrees above its south galactic pole direction, would appear as a flattened disk structure extending across much of the sky, its spiral arms, central bulge and disk thickness all visible in a single perspective that no photograph has ever captured. Our own galaxy seen from outside its plane is one of the great unachieved images in astronomy, and while a spacecraft could not travel to extragalactic distances in any practical time frame, the increasing perspective gained as it climbs to hundreds or thousands of light years above the ecliptic would progressively reveal more of the galaxy's three-dimensional structure in a way that complements the perspective from inside the disk. The solar system's portrait from below, an image that has never existed. Of all the things that a mission to high ecliptic southern latitudes would make possible, the one that is simultaneously the most scientifically and culturally significant is the simplest to describe. A photograph of the solar system taken from below, looking upward at the plane of the planets as a single, unified structure in a way that has never been captured. No such photograph exists. The famous family portrait of the solar system taken by Voyager 1 in 1990, showing Earth as a pale blue dot in a sunbeam, was taken from within the ecliptic plane at an angle that showed the inner solar system from the side rather than from below. Every subsequent image of any part of the solar system has similarly been taken from within the disk, or from vantages only slightly above or below it. The view from directly below, looking up at the full layout of the planetary orbits and the zodiacal dust disk spread against the background of the galaxy, does not exist in the photographic record of humanity. This missing image is not merely an aesthetic gap, it is a scientific gap of genuine consequence. The three-dimensional structure of the solar system, the relationships between the planetary orbital planes, the thickness and distribution of the zodiacal dust disk, the geometry of the outer belt of small bodies in the Kuiper belt as seen from outside rather than from inside, the layout of the cometary orbits that bring comets plunging through the inner solar system, the spatial relationship between the solar equatorial plane and the ecliptic, All of these are currently known from mathematical models and indirect measurements rather than from direct observation. A photograph from below the solar system would be the first direct observation of the solar system as a single object viewed from a perspective outside its own plane. The practical scientific value of this image extends beyond the emotional impact. The zodiacal dust disk seen in plan view from below would reveal its radial and azimuthal structure in a way that measurements from within the disk cannot. The dust bands associated with specific asteroid family collisions would appear as discrete ring-like enhancements at specific solar distances, superimposed on the general disk structure. The relationship between the dust distribution and the planetary orbits, specifically the ways in which each planet's gravity concentrates or depletes dust near its orbital resonances, would be directly visible rather than inferred from complex modelling of ecliptic observations. The outer boundary of the main dust disk, where the Kuiper belt begins to contribute its own population of cold dust grains, would be identifiable as a change in the disk's properties at a specific solar distance. The image would also show, for the first time, the solar system's appearance, as it would look to any civilization in the galaxy that might be observing it from a high ecliptic vantage. The question of what the solar system looks like to an outside observer is not entirely academic. It bears on the strategy for how we search for planetary systems around other stars and on how we interpret the observations we make. By understanding what our own planetary system looks like from outside its plane, we gain calibration for the interpretation of circumstellar disk observations made with telescopes like ALMA, the Hubble Space Telescope, and JWST, all of which observe other planetary systems from various angles to their orbital planes. The solar system, observed from below by a spacecraft we have built and deployed, would be the best calibrated example available of what a mature planetary system looks like from outside its own plane. There is also a deeper scientific value in seeing the solar system from outside its own architecture. Many of the most important discoveries in astronomy have resulted not from observing entirely new objects, but from observing familiar objects from a fundamentally different perspective. The Earth appeared different when photographed from orbit. The Moon appeared different when viewed from its far side. The planets appeared different when spacecraft moved from distant points of light to close-up worlds. A view from below the ecliptic would represent a comparable shift in perspective for the solar system itself. It would transform the system from a collection of individually studied objects into a single observable structure whose global organization could be examined directly. The resulting image would likely reveal features that current models do not predict. The history of astronomy provides many examples in which new vantage points exposed unexpected asymmetries, previously unseen structures, or relationships that were invisible from older perspectives. The zodiacal cloud may contain subtle warps, density variations, or resonant patterns produced by planetary perturbations over millions of years. The outer dust populations associated with the Kuiper belt may exhibit structures that have been blurred or hidden by our position within the disk. Even small deviations from existing models would provide valuable constraints on the long-term dynamical evolution of the solar system. Beyond its scientific utility, such an image would possess a rare explanatory power. The solar system is often described as a flat disk of planets orbiting a star, but this remains an abstraction for most people because no direct image exists to make the geometry intuitive. A photograph taken from high southern latitudes would show, in a single frame, the architecture that centuries of astronomy have reconstructed through mathematics and observation. It would be a scientific image in the strictest sense, containing measurable information about the structure of the solar system, but it would also be something more unusual. A picture capable of changing how humanity visualizes its place in space. For the first time, we would see our planetary system not from within it, but as a coherent object suspended against the larger backdrop of the galaxy. The solar system's blind spot. The direction directly below us, straight down through the floor of the solar system, perpendicular to the ecliptic plane, is not empty. It contains the south pole of the Sun, with its poorly observed magnetic structure and the source of the fast solar wind. It contains the southern heliosphere, a volume of space as large as everything above the ecliptic, but measured only in brief, partial passes by a single spacecraft over 20 years ago. It contains the southern boundary of the heliosphere, where the Sun's wind meets the interstellar medium in a geometry that no instrument has ever sampled directly. It contains a view of the zodiacal dust disk from outside, of the galaxy with the solar system's own foreground removed, and of the solar system itself as a whole object seen from a perspective that no photograph has ever captured. The obstacles to reaching this direction are real and significant. The inherited orbital velocity of 30 kilometers per second that every Earth-launched spacecraft carries must be redirected or compensated, and doing so requires either the patient accumulation of many gravity assists over many years, the counterintuitive strategy of falling first toward the Sun to extract the energy needed for a high-latitude departure, or the slow, steady push of a solar sail operating over years. None of these paths is easy. All of them are feasible. The engineering exists. The mission concepts have been designed in detail multiple times over several decades. What has been missing is the combination of scientific priority and institutional will needed to convert a design into hardware and hardware into flight. The Sun has been spinning above the ecliptic for 4.5 billion years, its polar regions cycling through their magnetic reversals, its fast wind streaming southward through the heliosphere, its southern boundary meeting the interstellar medium in a shape that models disagree about and data cannot yet resolve. None of this waits on our readiness to observe it. The processes continue whether or not any instrument is positioned to witness them. The question of when a spacecraft will finally travel directly below us, past the Sun's south pole, through the southern heliosphere, and toward the heliopause in the direction that nothing from Earth has ever meaningfully gone, is not a question about what is possible. It is a question about what we choose to make a priority. The direction below us is one of the last genuinely unexplored directions accessible to spacecraft within our own solar system. The exploration is overdue.